So in this short video, we're going to see what a covalent bond is and what the strength of the bond depends on. Well, first of all, let's take a chlorine molecule. It's in group 7, so it only needs to share one electron to gain a full outer shell. So that means a chlorine molecule only has one covalent bond, which is a shared pair of electrons. So that's the diagram we draw when we're explaining a covalent bond. But you forget quite often that there is a positive nucleus in the center, and that positive nucleus is going to be attracted to the shared pair of electrons, and that will bring the nucleus in towards the shared pair of electrons, and that is your strong covalent bond. So when we define any bond, the first thing is that always a strong electrostatic attraction between, then you've got to decide what it is, and for covalent bonds it's between the shared pair of electrons and the positive nuclei. So now let's look at what the strength of the bond depends on. Well, it depends on the bond length. The shorter the bond length, the stronger that bond is and the more energy you need to break it. So what changes the bond length? Well, first of all, if you increase the number of shared pairs of electrons between the atoms, that decreases the bond length. And secondly, if you reduce the atomic radius and also reduce the electron shielding. So let me take each of those at a time. So let's first look at the first one, which is increasing the number of shared pair of electrons between the atoms. If we take fluorine, we can look at fluorine and oxygen and nitrogen and compare them. Here we've got the bond, and here we've got the bond energy. And you can see that fluorine is in group 7. It only needs to share one electron to gain a full outer shell. So there's our shared pair of electrons. That will attract the nuclei, but not that much because there's only one shared pair of electrons. So that's got quite a long bond length, and so it's quite weak. Now, if we now take oxygen, oxygen is in group 6, so it needs 2 electrons extra to gain a full outer shell. So that means it has to share 2 electrons each, so it has 2 covalent bonds, and that's why it's got that double bond there. And so because it's got 2 shared pair of electrons, you've got a greater electron density in the center, and so that attracts the nuclei more, bringing them close together, so you have a shorter bond length. And finally, if we take nitrogen, you can see that nitrogen is in group 5, so needs to share 3 electrons, so it makes 3 covalent bonds. And therefore you've got a much higher electron density in the middle there, which has a larger electrostatic attraction to the positive nuclei, bringing them even closer. And so this makes the bonds even shorter, which increases the bond energy, the energy needed to break the bonds. So secondly, let's consider the idea of reducing the atomic radius and electron shielding. So this time we're going to look at group 7 atoms reacting with hydrogen. So if we start with hydrogen fluoride, that's got a bond energy of 569, and you can see they share 1 electron each. When you look at hydrogen chloride, they share 1 electron each, but this time, because chlorine has an extra shell, it's got a larger atomic radius, so the nuclei are further apart, but also there's electron shielding from this inner electron orbit, and therefore that attraction to the shared pair of electrons is less. So if we try and show this like that, that could be hydrogen fluoride, this would be hydrogen chloride with a longer bond length, and if we move down to hydrogen bromide, you can see the bond energy is even less. That means it needs less energy to break the bond. It's a weaker bond, and you can see quite clearly the atomic radius of bromine is even larger, and not only that, it's got 2 inner shells, which means you've got a lot more electron shielding. So therefore there's a much less attraction to the shared pair of electrons, so that makes the bond length even larger. The one thing you must be careful of is this is nothing to do with the melting and boiling points of these molecules, because unlike ionic bonds, these are simple molecules, And therefore, if you want to talk about the melting and boiling points, of course, what you've got to consider is the intermolecular forces between these molecules, and those have to be broken, not the covalent bonds. So be really careful not to fall into that trap in exam questions. We will look at intermolecular forces in another video.